I am Panagiotis Lymperopoulos, and I'm going to present to you our analysis, our research, dynamic computational analysis of Pentamode structures. My co-author is Efstathios Theotokoglou. And we are in the Department of Applied Mathematical and Physical Sciences in National Technical University of Athens. So, in this presentation, we are going to see a brief introduction over metamaterials, the numerical investigation, the results, and we're going to discuss them, and finally the conclusion. So, what are metamaterials? Metamaterials are materials with extreme properties not found in natural materials, like the negative Poisson ratio, the negative electric and magnetic coefficient. They can have programmable properties, and they are a subcategory of the composite materials. There are several types of mechanical metamaterials, like the auxetic metamaterials, the negative compressibility metamaterials, and the Pentamode metamaterials. The auxetic metamaterials have below the zero Poisson ratio, while the negative compressibility appear to decrease their size after tension and increase their size after compression. And finally, the Pentamode metamaterials, which are the one that we're going to see. I have also included at the bottom of each slide our references, where are we taking everything from. So Pentamodes are 3D lattice structures which are composed by rods, and they have low values of the ratio G to K, where G is the shear modulus and K is a bulk modulus. Because they have low values of the ratio G to K, they are also named as solid water. They can be used for seismic isolators and generally for vibration isolation and in bioengineering applications. Here you can see a typical Pentamode union cell, where D capital is a large diameter, D small is a small diameter, and A is the main dimension. Here you can see how we can fabricate them. We can fabricate them using 3D printers. As you can see, we can do in each dimension that we want. In this presentation, we are focusing on seismic waves, which are propagated through the Earth crust, and they have frequency between 0.0 Hz to 10 Hz. And the most catastrophic phenomena are between 0.01 Hz to 2 Hz. So the numerical investigation. Here you see some Pentamode structure that we have used. This is a more artistic approach as you see them, because we analyze them through a finite elements method using 3D beam elements. And as you can see, we have used 3 union cell towards x-axis, 1 towards y-axis, and we have used 1 layer, 2 layers, 3 layers, and 4 layers, with and without confinement plates. We have used as material steel with those properties. And now we are going to see the conversion of the algorithm. We have used this type of Pentamode, which has 60 millimeters. We have fully constrained the bottom nodes. We have constrained the z-axis displacement at the top nodes, and we have applied a force of 1.5 kilonewtons toward the x-axis at the top nodes. As you can see, the displacement we have increased from 1 element to 15 elements per rod. And as you can see, we have the same displacement at the top nodes. So the algorithm is converged, and we have used 4 elements per each rod. Now the results. At first, we will see a dynamic shear strength versus a static shear strength calculations. We have a Pentamode, as you can see here, with steel as material. The main dimension is 30 millimeters, and we have applied a displacement at the top nodes of 1 millimeter, and we have fully constrained the bottom nodes. And the frequency range from 0.01 hertz toward to 10 hertz. As you can see, the dynamic shear strength appears to decrease, but this decrease is considered significantly small. Now we will see some cases that we have tested. At first without confinement plates, and then with confinement plates. We have calculated the shear strength and the bulk strength for the 4 cases of height, of Pentamodes height. Yes. And now you see the shear strength. As you can see, the Pentamodes with NZ1 appears to have the higher value for the shear strength, and we have a discrepancy for the Pentamode with NZ4. Now the results for the bulk strength. We have the highest value for the bulk strength for Pentamodes with NZ1. And these are the results with confinement plates. As you see, as we have smaller values for the NZ, the shear strength appear to have increased value. We see that the 2 discrepancies for the NZ3 and NZ4, the values are the same as with the previous case without confinement plates, but for the NZ3, we have an increased value, so we cannot see very well what's going on. But if you see the values, they are very close. And these are the results for the bulk strength. We see that for NZ4, we have a decrease in bulk modulus, but it's considered small. And now for a thinner Pentamode, we have, as you can see, the values for the shear strength is lower than previously, and we see more discrepancies than the previous case. And these are the results for the bulk modulus. Now the results with confinement plates. As you see, the results are very high for the discrepancies. That's the reason you see the values of the shear strength so low. And these are the results for the bulk modulus. So we have tested different load frequencies with and without confinement plates. And we see some discrepancies after the third layer, as you can see. After NZ3, we have discrepancies. The shear strength and the bulk strength decrease its value as the NZ gets higher. And if we have thinner rods, the values for the bulk modulus and shear modulus, shear strength, have lower values, and we have more eigenfrequencies that we can see. the eigenfrequencies are the discrepancies. As future work, we are going to test more materials, more Pentamodes topologies, and also rho geometries. And this is our bibliography. And thanks a lot.